Let's apply integrals to finding an area. It's going to be an area of an object that we already know the answer to, so we can check our answer. It's going to be a semicircle. Well, actually, a quarter of a circle of radius 3. What is the area is what we're after. Now, we know how to find areas of circles, pi r squared. And therefore, we know how to find areas of semicircles and quarter circles. For a quarter circle, it would be pi r squared divided by 4. The area is known to be that. So that would be 9 pi over 4 for this example. But we want to try to use integrals to confirm that, because that might give us some skills that would help us attack harder problems. So we want to practice it with integrals. Now, the most natural thing to do would be to say, okay, I got to find the function whose graph looks like this, and I integrate that with respect to x. And that would be fine using the equation for this. For the full circle would be x squared plus y squared equals 3 squared, which is 9, and solving for y as a function of x. However, we're not going to do that either. Just to throw your curveball, instead of using thin, tall rectangles, we're going to use thin, wide rectangles. Partially just to illustrate that we can do it, and partially to illustrate problem-solving techniques that, once again, will apply to other situations. Chapter 8, Applications of Integrals, I think is probably the most important chapter for this class. This is the kind of thing you want to get the most skill out of for your future. It's not easy in general as we go through the chapter, but it is very important. It's something worth working at. So we're going to slice this with thin slice. And in fact, we imagine taking a knife and doing the slicing. Pretend my hand is the knife. I'm going to slice this with thin slices, horizontal in this case. Oh, one typical looking thin slice might look like this. And the big idea is to say the total area of this quarter circle should be the sum of a bunch of thin slice areas of these things. Sum of a bunch of areas of thin slices. But now we need to bring in some notation that gets a bit confusing. Let's call the y-coordinate of the lower part of the thin slice. How about just a plain old y? And let's call its height, its small height, delta y. The book draws the pictures kind of like this. This thin width or height is delta y. But it is the height of these thin slices. And let's give the base of this thin slice a name. Oh, how about b of y? B standing for base of the object. Base. Then you look at this picture for a while and you kind of say, squint your eyes and say, you know, that thin slice, that kind of looks like a rectangle. It's not a rectangle, right? The bottom and top and left sides are straight, but the right side is a curve. So it's not literally a rectangle, but let's pretend. Oh, convenient fictions. We're going to do it. Convenient fictions. Let's pretend that's a rectangle. What's its area? The area of the thin slice. I asked the physics professors what they call these things. Sometimes instead of calling them slices, they call them chunks. I don't know. It feels better to call it a slice instead of a chunk. You could call that, how about delta A? We're thinking of delta Y as being small. if delta y is really small, 10 to the negative 3, 10 to the negative 10 even, 10 to the negative 100 if you want to get extreme, then the area of the thin slice is also going to be small. Maybe we should call it delta A. Our approximate equation, assuming it's a rectangle, assume rectangular area, is that that's base times height, b of y times delta y. Base times height. Pretending it's a rectangle. By the way, the skinnier and skinnier it gets, the more and more it looks like a rectangle. Right? If delta y were 3, it would not be a rectangle at all. It's as delta y gets smaller, these things get skinnier, that they look more and more like rectangles. So this approximation, you could argue, gets better as delta y goes to 0. The total area of the entire region, the entire quarter circle, could be thought of as a sum of the little areas, delta A. So I wrote a capital sigma for summation. Should I write I goes from 1 to n? The book does at first, and so I will at first. But in the long run, they say, why bother? Because we're not really trying to do numerical integration here. We're trying to figure out what integral to do to get the answer. So they go ahead and they put I goes from 1 to n at first, and we could do that. We could put a subscript of I on the delta A to indicate that the delta A's are technically different. There's a delta A1, a delta A2, a delta A3, etc. And those delta AIs can be thought of as B of yi times delta y. But there's a sloppy version of that to say the total area, which, by the way, I meant to call that A, is a summation like this. And we don't bother with saying I goes from 1 to n. And we don't even bother with the subscripts. That's the sloppy version. I meant to have an A in here, a capital A. So again, at first, they write I goes from 1 to n. And then they say, okay, well, let's not bother doing that. Let's not bother with the i's. We're just trying to write down a general summation that is going to be a Riemann sum for some integral. And it's really the integral that we're after, and we want to do the integral. And that's what we do now. We let delta y go to 0. Remember, with integrals back in chapter 5 and also in chapter 7 with numerical integration, left-hand sum, right-hand sum, midpoint sum, etc., we let n go to infinity. The number of rectangles go to infinity. That's equivalent, if they all have the same width, to letting delta x go to 0. Here's a delta y. Let it go to 0. And we would say we effectively define the total area to be an integral. Of what function? Of b of y. So the b of y stays there, and it's kind of like the delta y morphs into a dy. Is it a literal morphing? Is it magic? No. Just feels like it. It's really nothing magical. It's really kind of boring. It's really a definition, effectively, that the integral is defined to be that limit if the limit exists. It's not quite accurate, but close enough for us. Over whatever interval that we need to do it over, y goes from, look at the picture, over this entire quarter circle, y is going from 0 to 3. So the directions in the book say to do this kind of thing. You'll see problems just like this on the homework, including on the homework due Friday. And they say, write down a Riemann sum approximation for the total area, like this. And then write down the integral you're going to have to do, and then do the integral. We do need to still figure out what b of y is. We'll come to that. Before we do that, though, I want to give you a bit of extra directions. I want you to write effectively an infinitesimal version of this. What do I mean? Instead of thinking of delta y as just a very small with 10 to the negative 3, 10 to the negative 10, maybe even 10 to the negative 100, pretend it's infinitesimally small, smaller than any positive number there is. But remember, that's a convenient fiction. No such numbers exist in the real number system. It's only pretend. And when you do that, it's traditional not to call it delta y anymore, but dy. And we're going to effectively write this equation, changing the deltas to d's, and changing the approximately equal to an exactly equal to. The infinitesimal version is that dA, the infinitesimally small area of the infinitesimally thin rectangle, equals b of y dy. And we really do think of it as an infinitesimal rectangle instead of an almost rectangle with a curved right side. That little part that makes it not a rectangle becomes less and less prominent as delta y gets smaller and smaller. So you might say that if you replace delta y with an infinitesimal, it literally becomes a rectangle. This is all imaginary math. I don't mean I, whose square is -1. I mean just all in your imagination. It's not rigorous math. Don't ever think it's rigorous math. Don't ever let a science or physics or engineering teacher tell you it's rigorous math. It's not. They may not be able to explain why it works. They just know it works. And it's nice, it's intuitive, it's fun, and it can get you the right answer if you're careful. There is always the nagging feeling, though, with more complicated problems, am I really doing this right? Experience is the way to go. What we do up here, we let delta y go to 0. Do I let dy go to 0? No, effectively, it's already 0. Or it's infinitesimal. So instead of saying let dy go to 0, we just say a is the integral of dA is the integral of b of y dy. Where this integral sign is really thought of as a sum. To find the total area, add up the infinitesimal areas. In this context, we imagine the integral as meaning sum. It's really not a sum. It's really a limit of Riemann sums, which is not the same thing as a sum. But we pretend. And being completely serious, we pretend it's a convenient fiction. A convenient fiction. Giving us this, you might call this equation here a conceptual equation. Conceptual equation. It's not a literal equality because essentially this symbol on the right doesn't have any meaning, any officially defined meaning. It's intuitive. Find the total area by adding up the little areas. That's how you think of it. And those little areas can be thought of as being products. B of y times dy. Areas of infinitesimally thin rectangles. We're adding up those areas. But then you say, wait a minute. How is this useful? Well, okay, if I'm actually going to do the integral, I need limits of integration. So then you just jump right to there. And you get the same integral and the same answer in the end anyway. It's a bit more fun to do it the infinitesimal way, a bit less fun to do it the Riemann sum way. Do it both ways on the homework. The book tells you to do it with the Riemann sum. I'm telling you to also use an infinitesimal approach. At least write this equation right there. as well as the Riemann sum, either with I going to 1 to n or not, and then write your integral and then do your integral. So in this case, let's go ahead and do the integral as quick as we can. We got to figure out what the b of y function is. Go back up to the picture. B of y is this base, this width here. At a given value of y, that's an x value along the curve. Solve this equation for x, not y. Subtract y squared from both sides, take the positive square root. X is going to be square root of 9 minus y squared. That's the b of y function. You might wonder, I picked y to be the lower coordinate of the thin slice. Could I pick the upper one? Yes, you could. It's not a big deal. Or the midpoint. We're not literally doing a numerical integration, though, so I don't really need to worry about it. So the b of y function is square root of 9 minus y squared. Yeah, we are using y instead of x. It's okay. To do this integral, we need a trig substitution. Y equals 3 sine theta. So dy is 3 cos theta d theta. Make those replacements. Get square root of 9 minus 9 sine squared theta times 3 cos theta d theta. If I'm going to write this as an equal sign here, I am picky. We need to change the limits of integration. This is equivalent to theta equaling inverse sine of y over 3. And that's going to be the equation that allows me to change my limits of integration. Though the lower limit stays the same, I replace y with 0. Inverse sine of 0 is still 0. But if I replace y with 3 down here, I get inverse sine of 1, which is not 3, it's pi over 2. So I have to change the limits of integration. This is going to be really handy in multivariable calculus when you're using, for example, polar coordinates, that you make these kind of changes. You don't practice it now, it'll be big problems in multivariable calculus. It's also technically required if you want equality. I emphasized this a couple weeks ago. This square root is the same as the square root of 9 cos squared theta, which in general is 3 times the absolute value of cos theta. But here, theta is between 0 and pi over 2 in the first quadrant. Cosine and sine are both positive there. I definitely can get rid of the square root, the absolute value signs. This is 3 cos theta, since theta is between 0 and pi over 2. Cosine is positive there. All right, keep going. So we end up integrating from 0 to pi over 2. 3 cos theta times 3 cos theta, 9 cos squared theta. We've done that before. Use a trig identity to write that as 9 halves plus 9 halves cos 2 theta. The 9 is coming from that 9, instead of having 1 half plus 1 half cos 2 theta. Almost done, getting close. Do the integral 9 halves theta plus 9/4 sine 2 theta. Theta goes from 0 to pi over 2. And the only thing that's non-zero is when you replace theta right there with pi over 2, giving you 9 pi over 4. Right? Because sine of 0 is 0. 2 times pi over 2 is pi. Sine of pi is also 0. Pi is 180 degrees. Plug in theta 0 there, I get 0. The only thing that gives you something non-zero is when theta is pi over 2 right there, giving you 9 pi over 4, which is the right answer. We got the right answer.